This video is on second order partial derivatives, and this is a continuation of the video on first order partial derivatives. So if you haven't watched that yet, it's imperative that you watch that before you watch this video, just so you understand where I'm getting the notation from and also how I'm taking derivatives. So for second order partial derivatives, just like we had, this is for functions of several variables. So when we had just one variable, we had first derivatives and second derivatives. So now we're going to have, first order partial derivatives and second order partial derivatives. And so if I gave you this, f with two subscripts x and x, this means take the second order partial derivative of f with respect to x and then with respect to x. So you might see the notation like this. You might also see it in the Leibniz notation with that curly d. So d with this little 2 up top, so it's the second derivative of f with respect to, and then x with this little 2 here means taking the derivative with respect to x twice. So this means take the derivative of f with respect to x. Right, so first we're going to take the first order derivative with respect to x. That's what the first x is telling you. All right, so you're doing that first. Then take the derivative of that. All right, so then take the derivative of that with respect to x. So first take the derivative with respect to x, and then you're taking the derivative of what you got with respect to x again. So this would be, one of the second order partial derivatives. There are other second order partial derivatives. Really, it's, first you could take the derivative of x and then with x, or you could take the derivative, right, with respect to x and then with respect to y, right? So this would mean take the derivative with respect to x first, and then you take the derivative of that with respect to y. So you do the first derivative with respect to x, and then the second partial derivative with respect to y from that, right? Or the notation on this, right, with the Leibniz notation would be with the curly d with the 2 superscript f, all right? So the second derivative with respect to f of, and then the order here, all right, with respect to x and then with respect to y. Right, I'm not going to write out the whole definition. I think you understand the idea. We also have what we would say is the first derivative with respect to y and then x. So it's saying take the first derivative with respect to y and then take the second derivative, right? So take the derivative of that with respect to x. Or the notation for this in Leibniz notation, again, with the curly d superscript 2 of f, right? So second derivative of f with respect to y first, then x. So you work it from left to right. Or lastly, you might see this as the first order derivative with respect to y, and then the second derivative with respect to y. So you would have the derivative with respect to y first, and then the derivative of that with respect to y. Or, in the Leibniz notation again, the second derivative with respect to y and then with the y. So you got that little 2 up there, right? So second derivatives. So basically, having an understanding what the notation means really tells you what to do. It's really that you work from the inside out, or you work from left to right. You're doing the derivative with respect to x first, then y if you're looking at this case. All right, if it was this case, the derivative first with respect to y and then x. And we'll take a look at some examples that use this. But it's important to have an understanding of what we're finding here. So, you're going to be doing what we did before. So if I said this, for an example, if I said find the second order partial derivatives for f of x comma y equals, maybe I'll do it down here so I have more space. For f of x comma y equals 3x squared y minus 2x plus 4y. Alright, so if I say find the second order partial derivatives for f of xy equals 3x squared y minus 2x plus 4y, first thing is you should recognize that there's going to be 4 second order partial derivatives, like we just described here, right, on the left. And additionally, to get to the second order partial derivatives, you first need the first derivative. So if I'm doing this, the first thing I'm going to do is find the first derivatives for this. So if I said I had the first derivative of f, right, with respect to x, so we're going to look for that first, the first order partial derivative with respect to x. Well, here's my function, the original function. Remember, x's are treated as variables, y's are treated as constants. So we have 3x squared y. The 3 and the y, right, are going to be constant, so they're going to stay. The derivative of the x squared, because that's a function, you bring the 2 down, it would be 2x, so 2x times 3y, that would give us 6xy, minus the derivative of 2x, right, with respect to x, would be just minus 2 times 1, which is minus 2, because the derivative of x is 1. Right, so it's a constant times a function, the constant stays, the derivative of the function is just 1. And then the derivative of 4y with respect to x, well, is this a constant or a function? Well, it's a constant because it doesn't have any x's in there, right? Y is treated as a constant, 4y is a constant, the derivative of a constant goes to 0. So the first derivative with respect to x is just 6xy minus 2. We also are going to need the first order partial derivative with respect to y. So y's are treated as variables or functions, and the x's are treated as constants. So if I have 3x squared y, the 3x squared, this is all a constant, all right, and y is the function. So 3x squared will stay as a constant in front times the derivative of y, which is 1. So let's just be 3x squared times 1, which is 3x squared. The derivative of negative 2x, well, we're taking derivatives with respect to y, so x, well, that's a constant, so 2x is a constant, derivative of a constant, that goes to 0, so I don't have to include that. And then the derivative of 4y with respect to y, well, that's going to be plus 4. So the first derivative with respect to y is going to be 3x squared plus 4. Now, once we have that, I didn't actually answer the question yet, right? I want the second order partial derivatives. So far I've only found the first order partial derivatives. So now we're going to look for the second order. So if I said I wanted, you know, the first one we talked about here, right? The first derivative with respect to x and the second with respect to x. Well, the first with respect to x, that's telling me to use this one. So that's what that first x is telling me. Use this first order partial derivative. Now I'm taking the derivative of that with respect to x. So I'm just looking at this. So what's the derivative of this with respect to x? Well, 6xy minus 2. The 6xy, the 6 and the y, right, if we're doing this with respect to x, 6 and y are constants, x is a function, so the derivative of x is going to be 1, so 1 times 6y is going to be 6y. The derivative of negative 2 with respect to x, well, it's a constant, so the derivative of that is 0, so the first one is just going to be 6y. The next one you want to look at, f of xy, right? So the first derivative with respect to x, that's what that's telling you to do there. And then the second derivative with respect to y. So first derivative with respect to x, that's using this one. The second one with respect to y is saying take the derivative of this with respect to y. Well, that means the 6xy, the 6x is going to be constant and the y is your function. So it'll be 6x times the derivative of y, so 6x times 1 would be 6x. And then the derivative of negative 2, again, is a constant with respect to y. It's going to be 0, right? Derivative of a constant is always 0. So this is just going to be f x then y is equal to 6x. Let's take a look at the other partial derivatives. I'll use yy first. So we're taking the derivative of fy, right? That's what the first y tells us. Use the first partial with respect to y and take the derivative of this with respect to y. Well, the derivative of 3x squared, well, 3x squared, that whole thing's a constant. There are no y's in it. So the derivative of a constant, that'll be 0, plus the derivative of 4, well, that's a constant, so the derivative of that with respect to y is also 0. So second derivative, right, with respect to y, that's 0. It's okay to get 0. Don't let that throw you off. Right, the partial derivative of this with respect to y, well, this is all a constant because there are no y's in there, so the derivative of that would be 0. And then lastly, we would have fyx. This is saying take the first order partial derivative with respect to y, that's here, and then take the derivative of that with respect to x. Well, the derivative of 3x squared with respect to x, that's a function, so the derivative of that would be, bring the 2 down, would be 6x, remember reducing the power by 1. The derivative of 4, well, that would be 0, and so you get f of yx equals 6x. Now, something to point out is that these came out the same. You should verify this like I just did. A lot of the times they will come out the same. Basically, if you have a smooth function, these will come out to the same partial derivatives for fxy and fyx. For the second order partial derivatives, but you should verify it doing the actual work for it because it's not the same work. The work is different to get to the answer, but they do come out the same. But you should verify it, you should make sure it works. We'll talk more about it in the next section, how we're going to use those. But most of the time these will look the same, but you should verify it and actually show the work for it. Let's take a look at one more. If I said I had this here, alright, so if I said find the second order partial derivatives for f of x, y equals, we'll say e to the xy power. Alright, so we're looking for the second order partial derivatives for f of xy equals e to the xy power. So again, first thing I need for my solution, well, I need the first order partial derivatives. So I need the first order partial derivative of f with respect to x. The derivative of e to the xy, it's a function because it has an x in there. When you have derivatives of e, remember you write exactly what you see. So derivative for a function of e would be e to the xy times the derivative of the exponent with respect to x in this case. So y is a constant, so it's a constant times a function because x is a function. And so the constant's going to say times the derivative of x, which is just going to be 1, so it's 1 times y, which is just times y. Which, you know, to make this a little easier to work with, right, we'll write as y e to the xy. For the first order partial derivative with respect to y, again, this is a function with respect to y because there's y's in it. This is, you know, a chain rule on e again. So derivatives of e, write exactly what you see. So we have e to the xy, you don't change the exponent at all, times the derivative of the exponent. Well, the derivative of the exponent is a constant, which is x, times a function, which is y, right? So derivative of the constant times a function, the constant stays, times the derivative of the function, derivative of y is just 1. So this will be times x. So for simplicity's sake, we write this as the first order with respect to y is equal to x e to the xy. Now once I have these, right, that's not actually what the question's asking. Don't stop here, sometimes people do. Right, those are just what you need to get to your next piece, which means I'm looking for the second order partial derivatives. So if I'm looking at this one here, we take the first one, I'll say f with x, x is the subscript. The first order derivative with respect to x, that's this one here. And I want to take the derivative of this with respect to x. That's what the second x means. So I'm using this one, that's what the first x tells me. With respect to x, that's what the second one tells me. So derivative of y e to the xy with respect to x, think about what's happening here. Y is a constant times e to the xy, which is a function. When you have a constant times a function, the constant stays in front, so we'll keep the constant. Times the derivative of the function, the derivative of e to the xy, well, derivatives of e write exactly what you see, so it's e to the xy, times the derivative of the exponent with respect to x. So x is a variable, y is a constant. So a variable times a constant, the derivative of x would just be 1 times the constant which stayed, so times 1y would just be times y. Alright, so this was the y in front times this is derivative of the function. And if we wanted to simplify that, we would have the second order derivative with respect to x. It's equal to y times y, which would be y squared e to the xy. The next one we'll look at, if I said I have the derivative of x with the derivative of y. So the first order partial derivative with respect to x, and we're taking the derivative of that with respect to y. So the first x tells me I'm using this first derivative. I'm taking derivatives of this with respect to y. Well, when you're looking at this, y is a function times e to the xy. Well, that's a function. So a function times a function, this is a product rule. All right, so be careful here, right? This is going to be a product rule now. So the derivative of the first, right? This y is a function, e to the xy is a function. A function times a function, remember the product rule says take the derivative of the first. So derivative of the first, derivative of y is 1 times, you leave the second alone, so times e to the xy, right? Plus the derivative of the second, so e to the xy, this is the second function. The derivative of e, right, exactly what you see. It's going to be a chain rule on e. So you'd have e to the xy times the derivative of the exponent. Again, with respect to y, x is a constant, y is a function. So the constant stays times y, the derivative of y, which is 1, so times x. And then you multiply this by the first. The first was just y, the first function. So if you're looking at your product rule, just to kind of, refresh where you're getting each piece from, all right, this is like your f prime, this is your g, this is like your g prime, this is your f, right? The derivative of the first times the second plus the derivative of the second times the first. All right, once you're here, you just have to simplify it. This gives us, we've got 1 times e to the xy is just e to the xy, plus here I've got xy, so x times y, e to the xy, and you can leave it like that. All right. And then the other two partial derivatives, if I was looking for f of y with respect to y, so the first order derivative with respect to y is here. We want to take the derivative of that with respect to y. So the first variable you see down here is telling you which derivative to use. So the first derivative is f with respect to y, and then you're taking derivatives of that with respect to y. Well, looking at this, x, well, that's a constant times e to the xy. Well, that's a function because it has a y in it. So a constant times a function, you keep the constant in front. So keep x times the derivative of this function part, e to the xy. Well, that's a chain rule on e, right? Exactly what you see, e to the xy times the derivative of the exponent. Remember, we're doing this with derivatives with respect to y. So x is a constant, and then y is a function. So the constant stays, the derivative of y is just 1, so this is just times x. And then, that's really it, right? Because it's the derivative of just the function. The constant stays in front, the derivative of e to the xy is just chain rule on e. So e to the xy times the derivative of xy with respect to y. Derivative of y is 1, the constant x stays in front. So simplifying this, you have x times x will give you x squared e to the xy, and that's it for that second order derivative. And then the last one we'll look at is f y x. Take the first order with respect to y, and then take the second derivative, right? So take the next derivative of that with respect to x. So the first y tells you which one to use. The second one tells you which variable to take the next derivative with respect to. So I'm taking the derivative of this x e to the xy with respect to x. Well, again, this is a function. X e to the xy is also a function because they both have x's in there. So that's a product rule. It's a product of functions, right? It's this function times this function now. So you have to use product rule, derivative of the first. So derivative of x with respect to x would be 1 times, you leave the second alone, so times e to the xy, plus the derivative of the second, well, that's e to the xy you have to use a chain rule on it. So derivatives of e, write exactly what you see, times the derivative of the exponent with respect to x. The derivative of xy, x is a variable, y is a constant, so the y is going to stay. The derivative of x would just be 1, so it's times 1y, so times y. And then you have to multiply that by the original first function, which is times x. So if you were doing your product rule on this, just to give you an idea, right, this would be your f prime, this is your g, this would be your g prime, the derivative of the second, times this would be your original first. Simplifying this, we get 1 times e to the xy is e to the xy, plus y times x, the same as saying xy e to the xy. And if you notice, these did end up being the same, but you know, we had to show it. It came out that way for different reasons. You know, the order you take those partial derivatives does matter. So don't just write down what it is. I need to see it. So these second order partial derivatives are really an extension of taking the first derivative, and then they're telling you to take the derivative of one of those first partial derivatives with respect to which variable. So when you see these, the first variable you see down here in the subscript is telling you which of the first derivatives to use. The second variable in here is telling you what to take the next derivative with respect to. So hopefully this clears things up on second order partial derivatives. Our next section will show us how we're going to use these.